All right. It looks like everybody, or at least several people have joined up now. Hello, welcome everyone, and thank you for attending this tutorial. I'm Alan Witkoff, a fellow at Maplesoft, and I'll be presenting this tutorial on series and limits. Okay, so all right, let's start off with something simple, a Taylor series. So we just compute the Taylor series of this function here, and it produces polynomial terms out to a specific order. It can be used to compute Taylor expansions out to a specified order. Here's an example of exponential expansion at about x equals 1. Okay, here is an example where we've specified the order in the command. That's one way of doing it. Another way of doing it is through the environment variable order, which you can set, and it will explicitly use the environment variable value to compute the Taylor series. So when we're dealing with abstract functions like f of x, where f is an unknown function, they're assumed to be analytic at every finite point and that the derivatives all exist. So it gives the Taylor series in this form. If we ask for a Taylor series, the tangent function at pi by 2, Taylor tells us that there is no Taylor expansion at the tri-series. So if we do tri-series, we get this series here where we see that what in fact we've gotten is the Laurent series because there's a pole of order 1 at pi by 2. And so this shows that the series command can be used for the more general form of series, more general than Taylor. Okay, moving on. When you use series for a finite expansion point, it attempts to provide a expansion that's valid for a complex disk about that expansion point, a disk in the complex plane. So if a more specific answer is desired, assumptions can be used. So in this first example, we're restricting that series expansion we just computed to the left half plane, right half plane, real values of x, and positive values of x. And we can see that we get a good simplification when we restrict to positive values of x because the sign function is determined. But computing directly with the appropriate assumptions is quicker. Asymptotic series. Okay, so Maple has the asympt command that can be used to compute asymptotic series or series about infinity. This can be used to understand the behavior of a function for large values of its argument. So in this case, we computed the asympt of 1 over 1 plus x squared, and the leading term of our series is 1 over x squared, which tells us that this roughly behaves as 1 over x squared for large values of x. Here's the asymptotic series for the gamma function. In this case, it's given in terms of fractional powers of 1 over x. And to show that, yes, this is just a series expansion about infinity, we can get exactly the same result with the call to series with infinity as an expansion point here. The series call can be used to compute an expansion at minus infinity as well. Now, a gotcha. Okay, so we're going to ask for the series of gamma of 1 over x at x equals 0. And under the assumption that x is positive, and it says here, when calling series gamma, unable to compute series. Why? Series has the restriction that for a finite expansion point, coefficients can only depend subpolynomially on the argument or on the variable that you're expanding with respect to. The asympt function doesn't have this restriction. So we can obtain a series of gamma of 1 over x by computing a series of gamma of y at y equals 0 and just transforming y goes to 1 over x. And this gives us a series expansion where the coefficients are not subpolynomial. So this is a way to get a more general series. So series expansions at infinity or minus infinity are always assumed real or on the real axis. To get a series expansion, a more general series expansion that's valid in a complex disk centered at the north pole of the Riemann sphere, you can do a change of variables, much like we did before. So here's one that's valid only for the positive real axis, the negative real axis. Now, this transformation here, well, we want arcsine of x at large values of its argument. We do the arcsine of y, or arcsine of 1 over y, at y equals 0. Now, series' mandate is to give us a series expansion that's valid in the complex disk about y equals 0. So we have that, and then we do a transformation. Y goes to 1 over x, and we get a solution that's valid at the north pole of the Riemann sphere. Okay? And we can verify that with the prior results we computed above by just using assumptions and assuming x is positive, x is negative. And we see that the results do in fact match as expected. Okay, next, I want to talk about a little bit about order and what order means. Order isn't really a fixed order that you're computing it out to. It's not the power of the term. What it is it's more like a working precision. If you were working with a fixed floating point, you'd have a certain number of digits to work with. Much the same way in series, you have a fixed number of terms. So this function here, we should have displayed that. This function here, we compute the series expansion, and we see that, in fact, we have an order span of only 4, even though we requested an order of 6. And this is because this expression here could have powers of 1 over x squared and 1 over x in it, but they cancel. So really, there's 2 vanishing terms off to the left here. One other thing about series is that series has the remember tables. So if you compute a higher order series and then ask to compute a lower order series afterwards, you'll get the higher order series back because it retains the highest order of that series that it previously computed for convenience. You can modify this by telling series to forget using the forget command, and you'll get the result that you might expect. Sometimes series can return an expression with a much higher order than requested. And this happens when intermediate terms all vanish, and series can detect that. So we requested an order of 4 series. So we expected to see something like an OX to the 4 term, but in fact, it's OX to the 9 here. And that's because all the coefficients between x to the 3rd and x to the 9 vanish. We can have the opposite problem as well if there's significant cancellation that occurs. So for this sine of tan of x minus tan of sine of x, if we ask for the 4th order series of this, we just get an order term. We have to bump it up to 8, or actually 7, but to get anything non-trivial. And you can see, if you compare the series of the individual terms in the difference, they match for the first 3 terms. So this is the first non-matching term, which corresponds to what we get as the result. Okay. Here's an example where we get an error. This error is because asking for the series expansion of this expression will get the series expansion of the denominator, and that is 0, or effectively 0. And we see that the series expansion gives us just basically an order 9 term. We can compute it if we bump the order up to 10. Okay, and the final series example, or simple series example, is what happens if we try to compute the series of something that's identically 0, and in that case, we get an order term out to the order requested. Okay, so that's a bit about series. Now, what about practical use of series? First application, we have this curve in x and y, and this is the 0 set given by implicit plot. And we're going to use series to get a solution of y in terms of x. We can use solve, and solve gives us 6 solutions. All roughly look about like this, with the exception of some signs. Now, when you call series with root of, the result that's returned is a specific root, one root that's arbitrarily chosen. And what's kind of neat about series is you can substitute this in as the value of y, get a series expansion to validate. So in this case, we substituted our solution for y into the original equation, and we could see that, yeah, it vanishes out to order 4. And this is what we'd expect. More interesting, at least to me, differential equations. So we have this nonlinear differential equation. We try and call dsolve, and we don't get a result. We can ask for the series solution, and we get 2 solutions out. And that's not that surprising for this nonlinear because it's a leading quadratic. So quadratics typically have 2 roots, and this, in this case, corresponds to these 2 solutions here. And again, we can use series to verify them. Okay. More interesting differential equation. We have this differential equation here. It's a singular second order differential equation, inhomogeneous. And we can ask for the series solution of this. And in this case, it gave us 2 independent solutions multiplied by arbitrary constants, one of which is unevaluatable at x equals 0, which is why it didn't give the solution in terms of y at 0 and y prime at 0. If the only thing we're interested in is something that with a finite value at 0, we can just use an initial condition to say, okay, I just want something with y0 starting at y0, a finite value, and we get the one solution here that this corresponds to. Just a quick bit, multivariate Taylor expansions. We can get multivariate Taylor expansions. This function a combination of sine and cosine. We can call M Taylor. And in this case, we're asking for the Taylor expansion at x equals 0 and y equals 0 to order 8. And x equals 1 and y equals 2 out to order 4. In this case, though, you're calling M Taylor instead of Taylor because you're telling it it's multivariate. There's also the multivariate power series exam package that could be used as an alternative approach for this. It uses lazy evaluation, and it also works with multiple variables. Now on to the second part, limits. We'll start with a nice simple one, something that's equivalent to just the evaluation. We're just finding the value of this expression as x goes to 0. Interesting thing, if we try to compute the asymptotic behavior of this function here, asympt gives us an error because it can't compute the series. But we can compute the limit of this expression as x goes to infinity. And this just shows us that limit can be more powerful than asympt when trying to determine, the behavior of something as it's going to infinity. But to be fair, it has less to do. It only has to compute effectively the leading term. Here's another example. Again, a limit of this function as x goes to infinity. And if we compare that to the asymptotic expansion, we see that, yeah, the constant term matches, which is what we expect. One other thing about limit, it can return in terms of a range. So in this case, we have this combination of functions that essentially don't die out. They're constantly changing. And the limit of this combination of functions here, it says it's between -2 and 2, but it's undeterministic. Okay. All right, one-sided limits. Okay, a couple words about domains of validity first. So as I mentioned earlier, series expansions are valid in a disk in the complex plane about the expansion point, and you can use assumptions to restrict this. Asympt always gives one-sided expansions that are valid only along the positive real axis. Limit gives a value that has to be valid from both sides by default. So as you approach from the left or the right, but it's always along also the real line. So if we ask for the limit of this function, e to the 1 over x, as x goes to 0, it returns undefined. And we can see why if we look at the plot. So we can see if we were approaching 0 from the left, this function is going towards 0. And if we're approaching it from the right, it goes up towards infinity. So this is where you use the additional arguments right and left to give a single-sided limit result. Now, you have to use left and right and not assumptions because x is a dummy, just like for definite integration. It's the same idea. We're eliminating x. So if you try to do this with assumptions, you'll get the same result as if you tried to do it without. Always remember using right and left. Now, limit is only really for continuous functions. So we have this discrete function here that say we've obtained somehow, and it's defined only for integer values of n. We can't directly compute the limit of that. But if we're lucky and simplification under integer assumptions gives us a continuous value or continuous function, we can compute the limit of that. Okay. Parametric limits. We can compute limits with parameters present. But when a parameter is present, it's assumed to be arbitrary and generic, or arbitrary complex value and generic. So if we compute the limit of x times gamma of x minus a as x goes to 0, we get 0. But if we do this for a specific value of a, 2, we get something that's not 0. 2 is an example of an isolated point where this is not true. And in fact, for this specific expression, this is not 0 only when a is a non-negative integer. And so we can ask for the limit under that assumption, and we get the expression we expect. Okay. Now, if we want to compute the limit of x to the n as x goes to 0 from the right for just an arbitrary n, it returns unevaluated. And if we assume n is positive or negative, we get very different values. For n positive, it's a 0, and negative, it's blowing up to infinity. Okay. This then demonstrates that we can call limit with the parametric argument. And what it'll do is it'll break down the possible values of the limit based upon values that it could determine it's different at for that parameter. Gives the results in terms of piecewise. Okay. All right. Multivariate limits are also possible in Maple. We have this function here. And if we ask for the limit of this function as x and y go to 0, it's undefined. Okay, and this is because if we look at these two expressions, the limit at 0 when you're approaching along the line x equals 1, this expression, this expression gives a 4. And approaching along the line y equals 0 gives a 1. So in fact, the reason that the limit doesn't exist is it has a different value depending on the angle of approach or direction of approach. And we can view that function locally, and we can see that, yeah, as you're going towards 0, you could be doing so along this crest or along the dip at the bottom. So we don't know what the value is if we don't know the direction. This is just a simple example to show that trivariate limits are also supported, any number of variables, really, if you can compute them. And one other note, multivariate limits are a lot trickier than you might think. So I've got this reference here where this example came from. So we have a nice simple rational, or I should say, a nice simple rational function of two polynomials in x and y. So, okay, let's try and manually compute the limit for this. And what I'm going to do is I'm going to say, okay, let's approach this along the line y equals mx. So the function along that line looks like this. And if we take the limit as x goes to 0 of this function, we get a 0. So what this is telling us is that if we approach the origin from any direction along a line, this function approaches 0 every time. So naturally, you would think that this means that the limit of this function at 0 is 0. But in fact, it's not. If we instead approach along a parabola, where now I've just replaced y with c times x squared, and then take the limit, we get an expression in terms of c. And we can compute the maximum and minimum of this to be minus a half and a half, respectively. Now, limit figures this out on its own. So it's got that the algorithm, the knowledge from this reference built in. And in fact, the minus a half and the half are the extreme quantities for this. And gosh, I went through that a lot faster than I expected. Anybody have questions? I see there are a few in the chat. At least one. Suppose you've calculated several series in a row. We'll forget, remove all of them, or just the last one. It's always all. Okay, and I see Austin answered that. Do we have any other questions? Okay. Well, I'm quite early, so
maybe I can pose a question.
okay.
I was interested in that example that you gave with e to the power x plus e to the minus x and
Okay.
parenthesis minus
All
e
right.
to the x. I was
That is
well, while you were talking about that, I was
okay.
trying to understand a bit more about it.
Okay.
Um,
That's the one where limit worked and asympt didn't, right?
that's right. Yes.
Yeah. Okay. So that should be in the. I will find it in a moment. Right here. Okay. This one.
Yes, that's the one.
Okay. All right.
So you saw that, or you showed that that limit comes up with the result
Yes.
1. And I was wondering if there's sort of a manual way that you can get more information about the asymptotic behavior. So I tried to take that expression and subtract 1 from it,
Yep.
and then multiply it by, let's say, x or x squared or things.
And did it give you anything? Because
Uh,
that's the first thing I'd have tried as well.
yeah. So I mean, let's do it. I mean, I just did it, so I know it will give a good result.
Okay. So we'll take the limit of this
Sorry,
minus 1 over x.
you want to multiply by x because we're
Oh,
going
sorry. Right.
to infinity, right? Yeah. Yeah. So that turns 0, and
Okay.
that's right. And then I tried with times x squared, and that also returns 0. And then I thought, well, there's a whole bunch of e to the x of e to the x things here. Would this be a higher degree? Exactly. That's exactly what I thought. And
There it
then
is. Okay. So yeah, you can, in this case, you're able to manually construct the series 1 plus e to the x, or 1 over, what was this? I forgot. So you want to go to infinity. And so it's going to be e to the minus 1 plus e to the minus x.
yeah, something like that. Yeah, that's
Yeah.
right. And then
Yeah.
right. So I
It's
was
a good,
wondering if you have any insights. Is there something that can transform this into an algorithm, or is this um, are we resigned to doing this manually, as it were?
well, I mean, yeah, I mean, the thing is, there was the intuition where you recognize that, oh, look, well, maybe I'll try exp, right? So I mean, there's a bit of an intuitive step there. I mean, maybe there's a possibility for creating an algorithm for this. Um, but I'm not sure right offhand. I mean, it might be good to mention why limit is stronger. Um, so the asympt has to, compute all the terms in a series, and I think it uses kind of an underlying recurrence type method for this. Limit uses this thing called MRV, or most rapidly varying term. And so it has a lot of specialized algorithms to be able to determine the behavior of the most rapidly varying term in an expression. And this is why it's stronger.
Right. Yeah.
I had something about that in the talk, but I cut it because I was worried for time. But yeah, so it's really limit MRV that's showing its strength here. But yeah, I mean, it's an interesting idea to come up with an algorithm for this to try to at least compute a couple of terms with the expansion. Because I mean, if you get it wrong, it'll go to infinity, right? And you'll be able to tell that you missed a term.
Yeah.
Yeah, it's a good point. Something to think about. Any other questions? Oh,
So
can
we
you
have,
multiply or divide two Taylor series to obtain the resultant series? Sure. Let's do that. Let's see. Let's take. Well, they have to be, of course, at the same expansion point. So I'll take this one, and I'll take this one. Oops. Let's not forget the x. Okay. And then I'll say, oops, what did I do wrong there?
You clicked on a Taylor of sign twice, so that, yeah.
Oh, right. Okay. No, this will work then. Uh, yeah, so you can do this. Again, this comes from the virtue of the fact that you can call series on an object containing series. So if you form the expression you're interested in, just call series on it to obtain the series you're looking for. Radius convergence.
I
Honestly, I'm not too sure.
I happen to know that in the development version we have that command today, but we didn't have it a month ago.
Okay.
So unless surprising things happen and we find irreparable bugs in it, this should be a feature of Maple 2025.
There you go. I was unaware, but that's good that we're going to get that too. Okay. I think that's probably my time anyway now. I'd like to pass this off to Stephen Forrest, who's going to talk about Maple with Jupyter and Python.